Star? What is a neutron star? No comments. Neutron stars are created when giant stars die in supernovae, and their cores collapse, with the protons and electrons essentially melting into each other to form neutrons. Neutron stars are city-sized stellar objects with a mass about 1.4 times that of the Sun. Born from the explosive death of another, larger stars, these tiny objects pack quite a punch. When stars 3 times as massive as the Sun explodes in a violent supernova, their outer layers can blow off in an often spectacular display, leaving behind a small, dense core that continues to collapse. Gravity presses the material in on itself so tightly that protons and electrons combine to make neutrons, yielding the name neutron star. This is how it is named neutron star. Ordinary stars maintain their spherical shape, because they have the gravity of their gigantic mass tries to pull their gas toward a central point, but it is balanced by the energy from nuclear fusion in their cores, which exerts an outward pressure. At the end of their lives, when stars are burned through their available fuel, their internal fusion reactions cease. The star's outer layers rapidly collapse inward, bouncing off the thick core, and then blasting out again as a violent supernova. After the star went supernova, the dense core continues to collapse, generating pressures so high that protons and electrons are squeezed together into neutrons, as well as lightweight particles called neutrinos that escape into the distant universe. The end result is a star whose mass is 90% neutrons, which can't be squeezed any tighter, and therefore the neutron star can't break down any further. Neutron stars pack their mass inside a 20-kilometer, 12.4 miles, diameter. They are so dense that a single teaspoon would weigh 1 billion tons, assuming you somehow managed to snag a sample without being captured by the body's strong gravitational pull. On average, gravity on a neutron star is 2 billion times stronger than gravity on Earth. In fact, it's strong enough to significantly bend radiation from the star in a process known as gravitational lensing, allowing astronomers to see some of the backsides of the star. The power from the supernova that birthed it gives the star an extremely quick rotation, causing it to spin several times in a second. Neutron stars can spin as fast as 43,000 times per minute, gradually slowing over time. The properties of neutron stars are utterly out of this world. A single teaspoon of neutron star material would weigh 1 billion tons. If you were to somehow stand on their surface without dying, you'd experience a force of gravity 2 billion times stronger than what you feel on Earth. An ordinary neutron star's magnetic field might be trillions of times stronger than Earth's. But some neutron stars have even more extreme magnetic fields, 1,000 or more times the average neutron star. This creates an object known as a magnetar. Starquakes on the surface of a magnetar, the equivalent of crustal movements on Earth that generate earthquakes, can release tremendous amounts of energy. In 1/10 of a second, a magnetar might produce more energy than the Sun has emitted in the last 100,000 years. Astronomers first theorized about the existence of these bizarre stellar entities in the 1930s, shortly after the neutron was discovered. But it wasn't until 1967 that scientists had good evidence for neutron stars in reality. A graduate student named Jocelyn Bell at the University of Cambridge in England noticed strange pulses in her radio telescope, arriving so regularly that at first, she thought they might be a signal from an alien civilization, according to the American Physical Society. The patterns turned out not to be ET, but rather radiation emitted by rapidly spinning neutron stars. If a neutron star is part of a binary system that survived the deadly blast from its supernova, or if it captured a passing companion, things can get even more interesting. If the second star is less massive than the Sun, it pulls mass from its companion into a Roche lobe, a balloon-like cloud of material that orbits the neutron star. Companion stars up to 10 times the Sun's mass create similar mass transfers that are more unstable and don't last as long. Stars more than 10 times as massive as the Sun transfer material in the form of a stellar wind. The material flows along the magnetic poles of the neutron star, creating X-ray pulsations as it is heated. By 2010, Approximately 1,800 pulsars had been identified through radio detection, with another 70 found by gamma rays. Some pulsars even have planets orbiting them, and some may turn into planets. Types of neutron stars. Radio pulsars. Recycled pulsars. Millisecond pulsars. Magnetar. Soft gamma-ray repeater. Anomalous X-ray pulsar. Low-mass X-ray binaries, LMXB. Intermediate-mass X-ray binaries, IMXB. High-mass X-ray binaries, HMXB. Accretion-powered pulsar.